Hello, everyone, and welcome to this session of the Spatial ML seminar. And today we are happy to have Juan Camilo Vega from U of T. So Camilo is a fourth year PhD student in the High Performance Reconfigurable Computing group in the ECE department of the University of Toronto. He's supervised by Professor Paul Chow, and his research interests are in studying multi-FPGA computation environment, their promises and scalability challenges, which he will talk to us about today. And he's currently leading a project called the Galapagos project within his research group, which he will give us a lot of details about today. So Camilo, thanks for making the time to be here.
Yeah,
And
thank you,
please
Andy.
take it away.
Yeah, thank you. So before we get started, I would really like to acknowledge the Galapagos team, both current and past members. Naif, who is in the talk, and he created the project, and a huge number of people who have all been contributing to the project. And today I'm going to be presenting the research of all of us of the team. This is not all my work. It's mostly not my work. So I just want to thank everyone for their great work in making this a reality. Um, I'll begin today by exploring our group's vision. Then we'll provide an overview of the Galapagos architecture, looking at all of its features and capabilities. And then, as this is a spatial ML talk, we will then talk about some of the projects involving ML that have been built using this platform. This will conclude kind of our completed work. But since this is an active work in research, we will then delve into what we're actually working on, the features that we're hoping to soon form as part of this infrastructure. And then we'll conclude this talk and offer acknowledgements. So let's talk about our vision. We're working with the standalone FPGA model, where the compute is primarily driven by the FPGA, rather than merely using an FPGA as a CPU accelerator, primarily by having it as a network-connected device. Now, we wish to enable the use of FPGAs as a first-class computing device to be able to leverage their high-speed SerDes for communication and omit the very high overhead, power-hungry CPU in our compute flow. And in this context, we want to enable the creation of multi-FPGA applications to extend the possibilities of what an FPGA can do. So we're not limited in scope to little applications that can fit in a single device. Now we are working on scaling these clusters up to support the size required by the very large data center scale applications, such as large language model training. And we don't wish for our architecture to prevent the use of any of the modern tools that are coming out that are becoming available. So let's talk a little bit about the architecture. In Galapagos, we are essentially programming an arbitrarily large FPGA device, something much larger than any FPGA on the market. And the way we do so is by implementing a series of kernels. And they're all going to be interconnected by this bidirectional connection to a virtual axis stream NOC. Let's call it the VNOC. Now we take this model, and then in our tools, we'll place it onto a series of FPGAs where it abstracts away their inter-FPGA networking. To the users, everything appears to be on the same device, even if maybe some are sharing, some aren't. And we could also have heterogeneity in this case. We can have FPGAs of different types. We can have some FPGA-based kernels, some software-based kernels, but the core tenet is that to a kernel, it just sees the virtual NOC connection and nothing else, and it doesn't have to care about how anything else in the network is implemented. Galapagos was built as a series of abstraction layers, mirroring what was done in the software scale, as shown from the physical hardware up through the FPGA version of an OS, which is the shell, some networking, and then finally communication between nodes. So let's look at each of these layers. On the physical side, we have widely different scales for different applications, from clusters of tiny edge devices shown on the left to larger compute clusters like the research cluster we have in Toronto shown in the middle. And to the right, we have the enormous data centers with thousands of devices that our dream is that one day may incorporate FPGA devices. So we aim to provide the solution as to how to extend FPGAs beyond the small-scale acceleration world to these larger clusters to allow us to build the very interesting large applications seen in ML. But I acknowledge research in this field is expensive, and many of your labs may not have the large cluster of FPGAs and a 100G switch to connect them all. However, we as a research body need to foster a spirit of collaboration and sharing of pooled resources. I'm very fortunate that my supervisor and our lab has provided me with a fairly extensive cluster of FPGAs. And as a result, we are already collaborating with other universities that utilize our devices to perform their Galapagos ML applications. Similarly, there's other groups that do this. There's the US National Science Foundation. They built the Open Cloud Test Bench, a huge cluster of FPGAs that's available for most research labs if they apply. They also have users from all over North America and Europe, so they allow for teams outside of the US to use their clusters. And there's also AMD themselves. They have been building these large FPGA and server clusters called hack centers. And currently they have centers in both Europe and North America. I think they have 2 in each and a 5th in Singapore. These clusters are meant for university research to be able to test their product. So even if your lab doesn't have a multi-FPGA system, you can still do experiments within this realm, and we hope that our tools are able to simplify that if you find that this is something that might be useful for your work. So going back to Galapagos, layer above the physical layer is the hypervisor, or kind of the OS of FPGAs. It's called Shell based on, I believe, Microsoft that coined the term, but this is essentially abstracting all the I/O interfaces and providing a uniform interface regardless of which FPGA you're targeting for the kernel user region. Essentially, you're given the different ports that form the VNOC. And we have a different shell for each FPGA that's automatically generated. And the idea is you can take your Verilog or your IP or whatever, and just tell us, okay, place it on this FPGA. And if your infrastructure changes and you ask me to place it on a different one, the tools can do that. And you don't have to worry about it because the shell will just change to the shell of that other FPGA. As alluded to earlier, we also have developed different types of kernels that can all be stitched together within this network. So we have the FPGA-centric kernels, which can be programmed in a variety of modes, from giving us a packaged IP to open mode, where you run our tools up to a point. A project opens up with a blank block design, just you see the VNOC interfaces as ports, and then you make your design and then click a button to keep running. You can give us HDL kernels. There's a variety of different forms, and if you can think of a different application space that might need a different form, we can always provide that for you. But we also have CPU software kernels that fit into the same space. We have HLS, which is actually really interesting because we can, by changing a single file in the XML, you can ask, can this HLS be run as an actual HLS in hardware or within an HLS simulator? And what this means is that you can create your large cluster, tell us, okay, but run our HLS as our simulation, and then you can test your stuff out. And once everything's working, you just change one line and everything moves down to hardware. And currently we're working on also AI engines, which is the new really cool thing that's coming out that enables really fast matrix multiplication and is really essential for anything ML. So we're building a kernel to target those. So above the hypervisor, we have the middleware, which is used to orchestrate our cluster of devices. So that this is automating the connections between the resources and basically finding a way to handle our entire cluster. So in the middleware, we take the kernels of whatever form they may be, it's very heterogeneous, and we take a small set of XML files describing how they should be placed, what should go well, where, as well as a description of the physical hardware available, the different physical nodes, the networking information, etc. Basically, to tell Galapagos this is the pool of actual resources we have to build our application. The middleware is a tool flow that takes those descriptions and then builds the bit streams for each of those devices, and the compiled code for the CPU device that can be then programmed to enable your project. As you can see, given kernels are of different sizes, we may end up with some of the kernels sharing the same physical device, though our abstraction means the user doesn't know or even care if what they're trying to speak is in the same device or in a different one. Now, a problem with middleware is partitioning, deciding which node goes where. And even in a very simple 3-kernel, 2-device examples where, let's say, 2 kernels fit into 1 device, we have 3 different options. So keep in mind that though functionally, there's no difference if the 2 kernels are on the same or different FPGA, the latency is not uniform. And as expected, it'll be a much lower overhead if communication is going to another node another kernel in the same node rather than a kernel in a different node. So one of our team members, Mohammed Mahdi, he built an automatic partitioner for this reason. It first takes a user-made naive partitioning, whose only constraint is the kernel mapping is legal, i.e. that there is sufficient area in each of their nodes to actually build the thing. It then allows Galapagos to run on that cluster, but sniffing the communication patterns in runtime. And then after looking at that for a while, it proposes a recommended partitioning scheme that is not only legal, but that optimizes communication. And as an example of this scheme, we built an AI application, and based on our bandwidth expectations, we thought that the optimal mapping between the 2 FPGAs is the mapping shown on the left. This mapping required, when running, a bandwidth of 1.2 billion packets per second on the network to be able to run. Then we ran the system, and after running it, it told us, no, actually, the optimal mapping is the one on the right, which is very similar, but with just 2 small changes. And once we did that, the bandwidth dropped to 821 million packets per second. The final layer is communication. The kernels are agnostic to the network protocol used. The user can, in a single setting, choose which protocol they want to use based on their throughput and latency, as well as what features do they want. For instance, do you want reliability to be built in? We currently support 100G UDP, 10G TCP, and 100G riffle. And you're probably wondering what riffle is. Sorry about that. So riffle is a network my colleague Clark Shen is developing to replace Ethernet in data centers. Now he has 2 versions of it, the better throughput 512 version and the better latency 256 version, but both are targeting 100G. Now this protocol is fully lossless as reliability is built into the physical layer of the protocol. You can assume that any packet sent in riffle will arrive to the destination without the need of a higher level protocol to implement reliability like TCP. And it does this while using only off-the-shelf Ethernet wires and unmodified transceivers. And as you can see, the throughput of both riffle versions on 100G link beat both Aurora and Interlaken, which are the other lossless protocols. But what is more impressive is the per hop latency of this protocol, which beats Aurora and is half that of CMAC and Interlaken. Unfortunately, this does require riffle-specific switches, for which we have FPGA bit streams that implement riffle switches on the many network port FPGAs. I unfortunately don't have much time to dive too deeply into the inner workings of riffle to show how it works, but I just wanted to give you a taste of its results, so you can see that it is a very interesting protocol, and I encourage you to read Clark Shen's paper on it and maybe talk to him if this is something that you find interesting. Of course, we also built a network abstraction layer, not just for the FPGA, but also for the kernels that are running on the server, of course, right? And this is in the form of the libgalapagos library imported by C or C++ code, which includes access to the virtual NOC among all the other functionalities that we want to give. This means that kernels can communicate with any other kernel in the exact same way, regardless of if the target kernel is a CPU or an FPGA one. In fact, the kernel itself may not even know what it's talking to. So this concludes the Galapagos project itself. Now let's talk a little bit about how it fits into the ML space. I will preface this section, the talk on AI Gen, by saying that I wasn't involved in the project. Actually, Naif, who's in the call, and Mohammed Mahdi were the principal drivers behind this project. AI Gen is a platform combining both HLS4ML and Galapagos. HLS4ML, it was this tool that was developed which takes a neural network model processed through PyTorch or any other training tool, and it takes a description of the available FPGA, of a single FPGA, and it uses those to create a synthesizable C++ HLS code, which fits within the described resource. What AI Gen did is it combined the Galapagos flow with HLS4ML, so we are no longer limited to having to fit the model into a single FPGA. Instead, now we're able to specify a small cluster of FPGAs and say, build me a model that fits there. Like Riffle, AI Gen would need its own separate talk to fully explain how it works. But the general tool flow is we are allowing the user to train their tool using really any of the ML training tools like Keras or PyTorch or any of those. We then take the JSON configuration file and HDF5 datasets that those give us, and we give them to a modified HLS4ML project. This works its magic, and then it produces a series of files, which are essentially the kernels, and the files separate to that indicates the layer and the data flow information. The layers and data flow then go through the partitioner, which optimally places the kernels in the available FPGAs. And then we have a tool to combine these two outputs and run Galapagos to finally obtain the bit streams to implement the requested neural network. As a sample application, our team used AI Gen to implement ResNet 50 in a multi-FPGA, and we were able to achieve excellent results. The latency, for instance, in FPGA-only configurations is as low as 1.9 milliseconds for a batch 1. And just to highlight how fast that is, if we just add a CPU at the endpoints to send and collect results, the latency goes up to 7 milliseconds, primarily because of the Linux stack. So we're performing an entire AI project faster than what Linux takes to just process the networking stack. This just serves to highlight how fast FPGAs can be and why it's so important to have this FPGA-only flows. When this was first built, we were targeting 12 FPGAs, but the team noticed that the area utilization could have been better. So a single line in the XML was modified to say, we don't want to target 12. Instead, we want to target 10 FPGAs instead of 12. Hit run, and Galapagos automatically built a 10 FPGA version. This serves to highlight how easy it is to use Galapagos to describe and modify our physical topology without requiring extensive recoding. We didn't have to remake any of the kernels, just a few XML lines. Also related to the AI world, but this time it wasn't actually built in AI Gen. Yu Gao and myself, we worked together. We built this fully unrolled iBert implementation on FPGAs. Here we are showing one of the 12 encoders that were built for this project. We were able to achieve a single encoder latency of 24.1 microseconds. And when we built all the layers, the full iBert model could run with an 860 microsecond latency. It's true that the NVIDIA 8100 still beat us, but we are getting closer to the performance results of GPUs with an earlier generation FPGA, and with further optimization, because this was mostly just a proof of concept, there's a lot of potential optimizations. I think we can actually start approaching the power of GPUs on FPGA world and hopefully exceed it. So now in this last section, I'm gonna showcase some of the new innovations that we're currently working on for Galapagos. Now, I do apologize in this section that I can't go into too many details because a lot of what I'm going to present here is unpublished. So I can only provide a very cursory explanation as this talk is going on YouTube to prevent the peer review process from failing. But I would be happy to talk with you all offline later if there's anything that you want to know more about in this section. So a concern with the VNOC is the scalability issues, which is really a problem anytime we're sharing a resource amongst many users. In this hypothetical, let's assume that the cost of maintaining each device-to-device link is a constant percentage of 0.1% of overhead. Even with this tiny per link cost, the overhead very quickly becomes the dominating resource user. And at one point, adding more computation devices actually reduces total overall compute power available. So we need to be very smart about how we scale to the very large scales that are needed for things like GPT training and so on. So to combat these scaling challenges, we are modifying our VNOC now to incorporate this concept called algorithmic distance or algorithmic locality between two nodes. Basically, the idea that two nodes won't necessarily speak to each other with the same frequency, two arbitrary nodes, but rather things that are close to each other in the algorithmic space will have much more communication than things that are far away. So we are enabling these different communication protocols. We're labeling low, medium, and long distance. Where low distance, these links are optimized for performance. We want throughput, we want latency to be excellent without any regard for how much the scaling costs. At the opposite end, we have these long distance links, which are much more numerous, that have extremely small overheads as we scale the number of devices, allowing for millions of devices, in fact, still with minimal routing overhead. But where we pay the price by lowering the latency a bit and increasing, by lowering the throughput, sorry, and increasing the latency. We'll also provision these reconfigurable medium distance links that are added at runtime, where we are allocating a fixed number of medium distance links to our switches that can be added anywhere at runtime, and a runtime profiler is sniffing at the long distance communication. And when it sees frequent communication pattern between two nodes initially labeled incorrectly as for long distance, it uses one of these medium distance links to speed up the communication from the two nodes. In terms of determining how we label them, it's actually trivially easy. As you can see, to identify which should be labeled as low distance versus high distance. Low distance, if two nodes on the same multi-headed attention are probably going to be low distance. They're going to be talking to each other very frequently. But if I take a node here and a node here, that's probably going to be a long distance link between them. So it's actually very easy for the user to identify and describe the between the low and the long distance. And then medium distance is figured out at runtime because the user might not be perfect. And the other project we're working on right now is the creation of a control memory interface to our VNOC, where it virtually appears as if there's an AXI master and AXI slave port in each of the kernels, allowing one kernel to set or read the memory mapped register within another kernel, or to target an off-chip memory. We are currently working actually on 3 different protocols with regards to this. We're working on a protocol for high distance or long distance links, one for low distance links, and one for control messages. But in essence, this is just meant to improve our control flow and to give our kernels better access to memory. And we are now also working on incorporating DDR and HBM to this flow. And we're just iterating through many approaches of how to implement this to find the optimal one. But this is a feature that we want to be adding in the near future. Also related to memory, we're also working on a disaggregated memory scheme. where memory used by one kernel does not necessarily need to reside on the same device of where that kernel is. Instead, we pull together all the memory in the cluster and have memory in the allocation scheme to improve resource utilization, while also incorporating concepts of caching to not lose too much in terms of latency and throughput when we go to disaggregated memory. So it's just another active project. And another priority of our group is we want to enable all the tools that are available out there. In particular, right now, there's a ton of attention to these VCK 5000 devices that have introduced AI engines, which have been shown to really be rather remarkable devices when it comes to matrix multiplication. So we want AI engines to also fit within the Galapagos framework, and we will do so by building these AI engine kernels that also have ports entering the VNOC. So essentially, we're creating this wrapper which bridges between the interface that AI engines need and the VNOC interface. And then we're adding all the tool flow to allow the user to give AI engine description files. So code comes in and it produces the necessary scripts to program the AI engines and to produce an output and automate everything in that space so that we can program these using the Galapagos flow natively like any other kernel. But this also raises a very interesting possibility. It means that a normal kernel that is using an AI engine accelerator may not actually even be in the same physical device as that AI engine. We might build an incredible matrix multiplier AI engine, and maybe in that same FPGA we can fit 3 other kernels that use matrix multiply, but we actually have 7 FPGAs that need matrix multiply, and they can all share that same AI engine, even though some might be off chip or even off device. And so this is extremely exciting work to see what possibilities this might do to improve our ML space. And in the spirit of resource sharing, like everything else in Galapagos, where we're splitting one FPGA to do many kernels, we also want to allow one FPGA, one AI engine array to become many little AI engine arrays if needed. So we're looking at the scheme of how the user can specify the different arrays, quarter it off, and then have multiple kernels on that same device. All right, so that concludes everything I wanted to say. So now let's just offer a brief conclusion. So ML models are becoming very large, too large for single device processing. So we need to think beyond the single device if we want to really be able to use some of the tools that are becoming available. Therefore, we present the Galapagos project as a platform to enable these multi-FPGA projects. Also, we continue to have ML and AI mindset. So we're trying to allow all of the AI tools users are familiar with to continue to operate with Galapagos, tools like PyTorch, or still allowing the AI engine support. And lastly, I want to encourage you to think about whether your research project may benefit from moving to the multi-FPGA scheme, even if you do not possess a cluster, and realize that there are many collaboration and research clusters available to borrow. So there's always the possibility to move into this scheme without too much of an investment on the part of your lab funds. I want to thank Xilinx for their boards and tools and consultation that has made this research possible, and want to thank the funding we have received from Alibaba, CMC, and OCI with Sienna. I'd like to open the floor with questions. I've put here some of the collaboration sites as well as our GitHub page. So thank you very much for your attention.